Konnichiwa friends, my name is Aisman Smasi and I welcome you to day 3 of the 100th days of deep learning practice. Okay, in this video we are going to learn about how to assemble neurons. Okay, this day will be very much important for our 100 days of deep learning, as in this video we are going to learn how we could assemble our neurons. Okay, so my expectation is this is that today we are going to learn about how to assemble the neuron. In next day we are going to learn about how to use the activation function, and in day 5 we are going to learn the full model class, okay, on how to make the full model in Torch. Okay, for now in this day we are going to learn how to assemble the neuron. Okay, before assembling the neuron we first need to understand what is a neuron. Okay, in deep learning a neuron is basically an mad version of a brain neuron that receives information and decide if it matters or not. If it matters, it passes it forward. Okay, so like it is basically an biological version where we could see here that this is an biological neuron and it is connected to every neuron from here. Okay, in the axon part, and here also from the dendrite part it is also connected to other neuron. Okay, once it get a signal, okay, it decides whether the signal is strong enough or not. Okay, and if it is strong enough, then it sends it forward. Okay, this is how an neuron works in biology. In deep learning it works exactly this same way. Okay, we have our inputs here as an tensor, we then pass it to an neuron, okay, which is basically a linear function with an activation function. Okay, then it checks whether to ignore it or pass it forward. Okay, and if it is strong enough signal, then the neuron pass the tensor forward. Okay, here it is basically difference between a brain neuron and artificial intelligence neuron. In brain it receives signals. In our deep learning it receives an tensor. Okay, here it signals strength and here we have our weights, okay, as an deciding factor. Here it uses a decision to fire, and in artificial intelligence it's basically an activation function. Okay, and fourth it sends a signal, and here in artificial neuron it outputs an value. Okay, so basically one neuron in our deep learning takes an tensor, then checks whether this strength or the weight is enough or not, and if it is, then it passes to the next neuron. Okay, so here you could see it's basically an deep learning neural network here. Okay, you could see here many neurons connected to each neurons from the backward and forward. Okay, it's basically like this. Here like this neuron is connected to every other neuron in the input feature and also this second hidden feature. Okay, so basically this is how an neuron work in deep learning. Okay, now we see types of neurons here. Okay, so we use various types of neuron depending upon the problem. Okay, for our basic problem we will generally use our linear, the flatten, the dropout, the batch normalization and the sequential. Okay, For most of our regression and classification, we use these types of neuron. Okay, for our computer vision we use convoluted neural network, okay, or the CNN. We have our convoluted one dimensional neuron, then our 2 dimension for pictures, and our 3D for an video, okay, and we also have our deconvolutional neural network. Then for our sequential data we have our RNN neuron, the LSTM and the GRU, okay. It's helpful for the problem where the sequence of the order matters, okay. Then for our transformer we have our attention layers, which are like embedding the multi-layer attention, the transformer encoded layer, the transformer decoded layer, okay. And other neurons include layer normalization, alpha dropout, the noise layer, the graph attention, and etc. Okay. For now, our in 100 days of deep learning practice will be focusing on these 4, okay, mainly. For now we are going to focus on the basic neuron, okay. Now next agenda is that how those neuron layer actually looks inside, okay. So this is an code of an making of a neural network in the PyTorch, okay. So first we import here torch, okay. First we import here torch, which is basically importing the PyTorch. Then we import the torch.nn, which is basically the short form of neural network, okay. So we import our torch.neural network as nn, which is basically a toolbox for building neural networks, okay. Every neural network that exists always exists within the torch.nn, okay. Then we create a class name, okay, and it takes our nn.module, okay. We create a class with neural network dot module, okay. Now you may be asking what is the module. So basically module here tell the PyTorch to track the weights and gradients, okay, inside this class. In this class, whatever the neural network we will build, it will keep tracking the weights and gradients automatically, okay. It will also add the GPU compatibility and also make sure that neural network is made whatever we will be defining inside the class, okay. So our nn module is very much important. Then we have 2 main function inside the class, okay. First is the dev init, which is basically a constructor which get initialized as soon as the class is called, and then we have the forward class, okay. So here in dev init we first call this super init module of the torch.neural network, okay. This is very much important to call the torch.neural network. Basically it's like saying that we are going to train and model and your job is to keep it ready, okay. Then we specify our neural layer, okay. So like if we want to use here linear, flatten, RNN, LSTM, we all initialize it here, okay. So this def init is used to define all our layers, okay. We are not stacking here, we are just defining the neural layer which we will be using in future, okay. Then we have our dev forward, okay. Here only basically we will be stacking the whole layers, okay. So first here you could see that first we stack the linear layer with an activation function, then we pass the x to an another layer. Okay, so basically the layer form is first an linear layer, then we have the activation function, and then we have the second linear layer. Okay, so here basically you could get a fair idea about the whole structure. First we import the torch and torch dot neural network, then we make in class where we have our two function, first is init and second is forward. In simple.nn we import it here nn.module, which is important for our automatic gradient calculation. In depth.init we first call the init function to make sure we tell the nn module that we are going to define layers here, and then we define layers, basically all the layers which we would need in future, and then in depth forward we stack all layer one by one for the whole mathematics path. Okay, then this one is not that important for now, as we will be seeing this in day 5. Okay, for now in this video we are going to learn how to basically stacking the layers together. Okay, now let's talk about the neurons here. Okay, so first is the linear layer. Okay, so linear layer is basically one of the most simple layer. Okay, here the formula it exists is basically output is equal to summation of weight into bias plus bias. Okay, here it's input. Okay, so first we, so like here the input is 3 and 3 and 5 as least, then we have our weights as 0.2 and 0.4, and then we have our bias as 0.1. Okay, so first we matrix multiply both the values. Okay, 3 with 0.2 and 5 with 0.4 here, and then we sum it together. Okay, summation, and then we add the bias here. Okay, this is a simple linear layer and will be useful in pure regression and pure classification tasks. Okay, so it's very simple here. I mean very simple layer. Okay, and here you may be asking is that how to define it. Okay, so it is defined by nn dot linear, and then we pass the input feature and the output feature. Okay, so here the nn comes from PyTorch dot nn. Okay, this one here we imported torch dot nn as nn. This nn is helpful for initializing linear layer or like any neural network layer. Okay, here we initialize it using this, and then here in first it's basically saying the what is the input shape of the tensor, and here in last is basically saying the output shape of the tensor. Okay, so basically if we have a neural network here, if it will take our two-dimensional tensor, then we'll be writing here nn dot linear 2, and if the output we should be getting is 10, then we will write here na dot linear 2 comma 10. okay, so basically it works this way. Also, the first rule in dimension matching rule is that you must check that here the shape between the two stacking neural layer. okay, here the output features of previous layer should be equal to our input feature of the next layer. okay, here this one is very much important, as here the output should be the our next layer input. okay, so this is basically how it works. okay, then we have our sequential layer. okay, this is not a like mathematics part here. Here it help in stacking path. okay, stacking path. So for example, if we have multiple layers, okay, like we have our linear layer 10 by 20 and we have our another linear layer 20 comma 5. okay, instead of just writing it this way, we could stack it together. okay, like here we pass the nn dot sequential as first nn dot linear 4 by 3, then our next linear layer, then our next linear layer, and then our final layer. okay, so it basically help in stacking path. Here we will see this in our practice session. okay, now how do we actually stack it? okay, first there are 3 ways to stack it. okay, first define all layer in the init. okay, here like inside the init we initialize our 2 linear layer. Here the output features should be same with input feature, which is practically the same. So then we passed our x as self dot fc1 for our first linear layer, then here the x we got as first layer, then we send the first linear layer to our second linear layer. okay, so we have our input, then we have our fc1, and then we have our fc2. okay, this is how we define. okay, the first option. Second option, we could directly initialize x here with directly. okay, first we will pass the x with the first linear layer, then we pass it to this second linear layer, and we could get the value directly. okay, this is also an option. And the third option is that we use direct sequential here. okay, so we make an fc1 with nn dot sequential, we pass both the neural layer, and here we just call out this layer. okay, and the whole thing is done in the same way. okay, so basically this is how we stack in the simplest way possible. okay, now you may be asking that suppose we could add here like any number. okay, like here we have like 8 as an input tensor, then we sequentially to our 1000, then to our 10 lakhs or something to etc. okay, so we could do this. Just you need to have one rule in mind, is that the output feature of previous layer should be input feature of next layer. okay, here the input tensor is 8, which is okay, then here 100 of the previous layer should be equal to 100 of the input layer, and then here also the same, and here also the same, and finally we want to get the output in 10 numbers, so we write here 10. Okay, so our input shape was 8-dimensional tensor and the output shape is 10-dimensional tensor. Okay, now we move on to our next layer, which is basically dropout layer. Okay, this basically randomly turns off neuron during training. Okay, so like if we here in between, if we had added an dropout layer, it will be basically killing values. Okay, like here when we do NN of dropout, p equals to 0.5%, it is basically saying to turn off 50% neuron. Okay, so if we'll be getting values like 10, 20, 30, 40, we randomly kills 50% values here and we get this output. Okay, this is very much helpful to prevent overfitting. Okay, basically it help our neuron, help our different path of neuron to learn it. Okay, rather than relying on a single neuron to learn. Now next come is the flatten layer. Okay, this basically receive data into a single line. Okay, nothing much. Like we have here 2x2 matrix, the flatten stack it into an single dimension. Okay, it is very much helpful in our CNN path. Okay, in our computer vision, whereas the neural network expects one dimensional input and the images or the videos we get in 2D or 3D, it's helpful to stack it into an 1D input. Okay, now we have here batch dot normalization. Okay, it basically help us to rescale the value. Okay, so learning doesn't go crazy. So like if you like add here like bn equals to n dot batch nor one dimensional 3, if we had this value, it works this same way as this scaling in machine learning. Okay, so we basically here scale the entire tensor to n small value, so like our learning doesn't go crazy on the very large value. Okay, it basically have the same meaning but this safer range. Okay, so concluding it all together, we could make a neuron by basically importing first NN dot sequential, which is basically stacking the neuron inside it. First we do flatten here, which convert in matrix or high dimensional tensor to 1D input. Then we have our linear layer, then we have our batch dot normalization layer, which basically stabilize. Then we have our dropout layer, which prevent overfitting. Then we finally have our linear layer. Okay, and here the output and input should be same. Okay, here do check it. Okay, now the question you may be asking is that how we could find that for a linear layer what will be our x and y. Okay, so first let's talk about what would be y. Okay, so y depends on completely on the output value. Okay, here if like it is a regression task, then you will always put the output as 1. Okay, so like 10-1 or like 2-1, depends on the task. Okay, if it is regression, we are considering only one output, and for classification it depends on the number of classes. Okay, so for example, if you want to classify two values here, the output value will be 2. If it is 10 multiple classification, the output value will be 10, and so on. Okay, so then this is how basically we'll be getting y here. For x here, it depends on the incoming tensor part. Okay, first thing first is that 0-dimensional tensor doesn't work here. Okay, you must understand, this is that tensor, as it's an neural network, it can't work in a single number. Okay, it needs a list of number as matrix or tensor. Okay, so this one will not work here, since here we are getting 3 numbers here. Okay, so here the input will always be y3. Okay, basically it operates on the last dimension of a tensor part here. Okay, so like here it's basically 3 by 1 is the shape, then here the 3 will be our input value in our linear layer. Okay, here this is an 2 cross 3 matrix. Okay, so here the last part 3 will be our input value for our linear layer. Okay, here the shape will be basically 2 cross 3 only na, so here the last part will define our input tensor. What happen if we do the random with 4, 10 and 8? So we will get the shape like this. Okay, 4, 10, 8 only. Okay, and here the last value will define the input shape of the linear layer. Okay, this part. So here in short, the input feature depend on the last dimension of a tensor, and the output depend on the task. Okay, if it is regression, you will be getting one value. If it is an classification task, you will be getting n values. Okay, so I hope you may not understand something fully during our session, and that is okay, because this stacking thing and the layer thing is well understood in the practice session. Okay, so see you in practice session today, where we'll be doing some practicals and we'll be fully understanding the 3 things here. Okay, also remember that neural stacking is fundamental for whole DA, so don't skip it. Okay, that's all for today. Thank you and bye bye.